Good day once again, students. Today we are going to talk about the motor effect. The motor effect. We all know from our IGCSE, GCSE or O level that when a current carrying conductor is placed in the magnetic field, then the two fields will interact, and when they interact, the interaction brings about a resultant force, and this resultant force causes motion of that particular current carrying conductor. We also know that when a charged particle enters a magnetic field at right angle, then it will move in one direction. If it was entering the magnetic field straight, it's going to bend. That is, it will change direction. So, a current carrying conductor in the magnetic field will move because of the influence of a resultant force on it. Again, a particle moving into the magnetic field at right angle will also experience the same force, and this will cause a change in direction of this particle. So we know now, this is just a reminder for us. This is just what we already know before from IGCSE qualitatively. So what should we bother ourselves about? We should bother ourselves today about the magnitude of this force which causes the motion, the resultant force which causes the motion, and the direction of the force. The direction of the force is something you already know using the Fleming's left-hand rule. We are going to continue to use that for the direction of the force. So we say motion is produced when electric field and magnetic field overlap at right angle. This can be seen when a current carrying conductor is placed in a magnetic field at right angle, or when a charged particle moves in the magnetic field at right angle. The movement is caused by a resultant force which is produced from the interaction of the two fields. You remember the catapult effect. We know that the current carrying conductor has a magnetic field around it, so it is now in another magnetic field, so there will be the interaction of the two magnetic fields, and this produces a resultant force, and this resultant force causes that particular current carrying conductor to move in a particular direction. The same thing with charged particle. So let's look at the direction. Let me remind you about the direction of this force we are talking about. The direction of the force. Remember, in my last video, I used thumb. Remember that when I was teaching this in IGCSE. But now I have another thing which you will remember more. We know the thumb. Don't forget, I'll stretch your left fingers. The thumb, the first finger, and the middle finger. The thumb, first finger, and the middle finger. When you stretch them at right angle to each other, this is the magnetic field. This is the force. Magnetic field, the force, and this is the current. So we say McDonald's fried chicken. McDonald's fried chicken. McDonald's fried chicken. McDonald's magnetic field. Fried force. Chicken, depending on you. Some people prefer to call this one field and call this one motion. No problem. It still goes. They prefer to call that one some people prefer to call this one This is chicken, sure, current. Some people prefer to call this one field, because we are talking about magnetic field, and they call this one motion. No problem. So McDonald's fried chicken, the way you want to call it, McDonald's fried chicken, McDonald's fried chicken, McDonald's fried chicken, depending on you. Once you remember McDonald's fried chicken and you know which one is fried, which one is filled, McDonald's fried chicken, McDonald's fried chicken. Okay, now, or Mama fried chicken, you can call it anything you want to call it. So they must be at right angle to each other. Now, when we look at this is just a reminder. If this is like this, placed like this, nothing happens because it is placed at angle 0. It's not at right angle. As you start curving it, bending it, as it is getting closer to 90, then the force will start. The force, then when it is 90 degrees, that means it's like I'm putting that same body like this, just like my pen, like this, in the magnetic field. Either it is taking current into the magnetic field or bringing current out of the look at it, into the board, or is bringing current out of the board, into the board, out of the board. Okay, if we want to look at that, we look at it this way. So for it to be perfectly at 90 degrees, if we do this, once you see this cross like this, it means into your page, across, into your page, across into your page means magnetic field is going in, and if it is current, it means current is going in. When you see a dot or a dot with a circle, it means that particular current is coming out, or if it is magnetic field, it means it's coming out of your page or out of the board. So when I do this like this now, it means the current here is in a conductor or which is going inside the board. Now, where will the wire go? You already know. Using Fleming's left-hand rule, you know the current is going in and the magnetic field this way, wire goes down. You know all this. And if the current is coming out, you know what to do. Place this there and you do the same thing using Fleming's left-hand rule. So when it is like this, that means this is magnetic field for you. Magnetic field here is going into the board, going into the board. Magnetic field B into board. Magnetic field in, out of board, out of my board. This is coming out, this is going in. So if I have this wire like this in this magnetic field, of course magnetic field is going in and current in the wire. It depends on where I have the current in the wire. Let's assume the current in my wire is going like this. Like this, it goes in and it comes like that. So this is the direction of current, this is the direction of magnetic field. That wire will go up. Here, if I bring the same wire here, current going in this direction, so the same way current going this direction and magnetic field coming, current going this direction, magnetic field coming out, current going this direction, magnetic field is coming out of the board. So where does this move? Down. The wire moves down. Don't forget that. Again here, wire carrying current this way, magnetic field that way, and it moves up. Don't forget that. So let's look at moving charge. Charge moving in the magnetic field. Let's look at positive charge first. This is a positron. This is a positron and this is a proton. A positron is the antimatter of the electron. So anti-electron, this is proton. Let's assume this proton is streaming into the magnetic field like this. It goes into the magnetic field. What happens to it in the magnetic field? Of course, it's going to change direction in the magnetic field. Where does it go? Does it bend upward or downward? What will you use? Fleming's left-hand rule. It's a positive charge, don't forget that. Positive charge move in the direction of current because current flow from positive to negative. So positive charge moves in the direction of current. So positive charge is moving that way, and magnetic field is coming out. Positive charge is moving this way because current, that means current is moving that way. Magnetic field is coming to you. So what do you have? You have it going down. In the magnetic field, it goes down. In the magnetic field, as it enters the magnetic field, it goes down. You can see what it is tracing. It is tracing a path. That path looks like what? It's a curve. It's tracing a curve. A curve is traced, and that curve, of course, as is magnetic, the magnetic field is perpendicular. The force on it is the force on this. The magnetic force there is perpendicular. It's perpendicular to it. So what does that tell you? This looks like a centripetal force, and we are going to talk about that soon. So if it is here, if it is going in here, if it's going into the magnetic field here, when the magnetic force is coming out, magnetic field there, when the magnetic field there, magnetic field in, out, and current that way. Magnetic field out, current that way. And this magnetic field in, current the same direction, so that goes up. That goes up. Magnetic field in, current in the same direction, this goes up. Don't forget that. A positron will behave like a proton. An helium will behave like an helium atom is positive, will behave like a proton. Will behave like a proton. However, an electron, which is negative, will behave the opposite way. When you place an electron here, when the electron is going in there, it doesn't mean current is going in that way. Current is in the opposite direction to the electron. Current is in the opposite direction to the electron. Yes, this is still go in, but when you are now talking about the Fleming's left-hand rule, when you are talking about the Fleming's rule, this time you will be talking about the electron going opposite direction of current, because it is negative, so it goes opposite to current. So when electrons goes in that way, so how will current move? Electron moving in that way, how will the current move? Of course, all these things I'm talking about, they are all just IGCSE revision. That's why I'm rushing them. They are all IGCSE or GCSE or O-level revision. That's why I'm rushing them. So when the electron is going in this way, that means current is going the opposite direction. Current is in the opposite direction. Yes, electron is moving this way, negative charge moving in. That means current is outside. So we say this chicken is out. Magnetic field is this way. Magnetic field is this way, coming out of the board. So what do you see? Then electrons will go that way. Again, current is this way because electron is entering that way. So current will be coming this way. So magnetic field is coming out, and therefore the force or the motion is that way. And of course, it's also still perpendicular. It's still perpendicular to the direction of motion. So now we have seen how the charges will behave. Quickly, let me quickly look at this before I continue. If I have two wires placed in the magnetic field, let's assume current flows up in this wire and current flows up in this wire. What do I see? Current flowing up. When current flows up in this wire, the right hand grip rule, don't forget that there will be anti-clockwise motion of magnetic field there. Anti-clockwise motion of magnetic field in that area. So anti-clockwise. And here, current is also going up. So what do we see? We see a clockwise. You see an anti-clockwise also. Look at it, anti-clockwise also. So anti-clockwise. We also see anti-clockwise. So what do we really see in real life? So when you have this current moving in the same direction, we see a shape like this. We see a shape like this. We see a shape like this. Look at it. What I'm showing you now is this wire. There's a wire into the board, and there's another wire moving current into the board. So into and into. So then along the plane of my board, there will be magnetic field. There will be magnetic field. Wire moving current in and the wire moving current in. Along the plane of my board, there is magnetic field, and this magnetic field has this shape, and that's what we will have here. That shape is what we will have here if I turn that thing to you. If I turn it to you this way. So wires carrying current in the same direction. This is the shape you have. Wires carrying current in the same direction. Now, wires carrying current opposite each other. Wires carrying current opposite each other. You imagine this was like this. That means my grip rule here will be different. My grip rule here will be different. So this is still correct. That's still correct. But for this, I'll have a different direction. For this, I'm going to have like this. So in a clockwise direction. Don't forget that. Grip rule in a clockwise direction. What have you seen? You have seen this. So what does this and this tell you? It tells you that the force there in this one is that of what? There is a force here and there is a force there. So the force here is that of attraction. That of attraction. So there's an attractive force this way. It's an attractive force this way, and current in the same direction. Current moving the same direction. And the other one, there is a repulsion. There's a repulsion. We have repulsion. Current in opposite direction. So current moving in there and current moving out here. So we see a repulsion. We see a repulsion. So that of attraction and that of repulsion. You see attraction and you see repulsion. Attraction, repulsion. Force of repulsion and force of attraction. Now, what is the magnitude of the force? What is the magnitude of the force we are talking about? This force we are talking about when a magnetic field, when a wire carrying current or a conductor carrying current is placed in the magnetic field, or a charged particle is meant to move or to travel in the magnetic field. So there will be a resultant force. The magnitude of that force when it comes to wire, let's look at the wire force or the conductor, straight conductor, depends on the magnetic field in that area, depends on the current in that conductor, and it depends on the length of that conductor in the magnetic field, and it also depends on whether the conductor is placed perpendicularly in the magnetic field or otherwise. If it is not placed perpendicularly in the magnetic field, you will have to resolve the component, the perpendicular component of it to the magnetic field. We are coming to that. Now, this force we are talking about is proportional to this, proportional to this, proportional to this. So it has a relationship with B, with I, with L, and we see that force is equals to B multiplied by I multiplied by L. B multiplied by I multiplied by L. So, but the wire and the magnetic field must be at right angle. Must be at right angle. If they are not at right angle, what happens? If they are not at right angle, what happens? If they are not at right angle, we have a situation where that's the wire, that's the magnetic field. Let's assume the wire is like that. In the magnetic field, it is carrying current that way. In the magnetic field is carrying current that way. Then we have to resolve into the component. So let's say it's happening at an angle of theta to the horizontal, as an angle to the magnetic field. Okay, if it is placed like this, it's perpendicular to the magnetic field, but you turn it away from perpendicular direction by angle theta. So now, what will be the new thing we will be talking about? We will be talking about this part. So, and this part, if this is I, this will be I sine theta. I sine theta. I is flowing through that. That will be I sine theta. So instead of us to have BIL, we have, or we say L sine theta, if you want to consider the length, L sine theta, the perpendicular component of it, which is B. So we now have BIL sine theta. F, in that case, this is 90 degrees. So BIL sine theta at theta degrees to the horizontal. At theta degrees to the horizontal. So this is what you have. BIL 90 at 90 degrees. So, but at angle theta to the horizontal, we have F equals to BIL sine theta. Somebody will ask me, okay, what about that conductor, charge particle moving in the field? If the charge particle does not move, then there is no current. If the charge particle moves, then there is current. So even in that wire, charge particles are moving. That's why there is current. So the original thing is actually movement of charge particles. So how does current relate to charge particle movement? So if we say if I say that the force we are talking about is BIL, but current is related to charge by what? By Q over T equals to I. So I can rearrange this to say F equals to B multiplied by Q over T multiplied by L. So, but don't forget, I like to push this one to this side. It doesn't really matter where I put it. Both of them are all downstairs there. B times Q multiplied by L over T. Don't forget, L is length. The length move, the amount of the distance moved by the particle in the magnetic field. The distance moved by the charged particle in the magnetic field is L. Don't forget that. L is the distance moved by the charged particle in the magnetic field. You can write that one down so you don't forget. Now, what do I have? L divided by T is like a distance over time, or displacement over time, which is equals to speed. So instead of writing this, I can as well write that F equals to BQV. BQV. Some people will write it as small letter q or BQV. And if that's charge, so F equals to BQV. For what? For a charged particle moving in the magnetic field, the magnitude of the force on that charged particle depends on the magnetic field, the charge, the magnitude of the charge on that particular particle, and the speed with which it enters the magnetic, which it moves in the magnetic field, with which it enters the magnetic field. Don't forget that. Now that we have seen this, what if that charge is an electron? Then F becomes equals to BeV. So you can also see this. V is the speed, Q or E, the magnitude of the charge on the particle, and B, the magnetic field. If that happens, that means, I hope you have written this down. Good. Now that means we can also write those that are at angle theta to the horizontal. Angle theta to the horizontal, we can also write that F equals to BeV sine theta, or F equals to BQV sine theta. So same thing, we can write that way. This is the magnitude of the force. I know you know the direction of the force. I know I wasted time talking about the direction again and again and again, but you have, at least it's a revision for you. Now you have seen that the magnitude of the force we are talking about. If that is the magnitude of the force we are talking about, I told you earlier that I will redefine magnetic flux density. I will redefine magnetic flux density. I wish to define magnetic flux density now in terms of B, in terms of length of the wire in the field carrying. Now, B equals to, if BIL is F, so B equals to F over IL. So I can now say the magnetic flux density, B, at a point in space is the force experienced per unit length of a long straight conductor, per unit length of a long straight conductor, force per unit length of a long straight conductor carrying a unit current at right angle to the field. So B, the magnetic flux density, can also be defined as the force experienced per unit length of a long straight conductor carrying a unit what? A unit current, perpendicular or at right angle to the field. We can also define it like that. Actually, some examiners want it this way. They want it this way instead of defining it with a flux. Instead of defining it with flux and area, some examiner actually want it this way. So it depends on the your board. So check some of your past questions and you see if this is what they want, you define it like that. I have given you the two possible definitions at your level. Now, today we have seen the force on a current carrying conductor, and we have seen the we have revised the direction of this force, and we have also talked about the magnitude of the force, and we also talked about the magnitude of the force of on the a charged particle going into the magnetic field. We have talked about the force acting on it, and we have also talked about the magnitude and the direction of the force. Now, before I go on, I want you to look back at one thing. Now, the magnetic field here is in the plane of the paper. The magnetic field here is into the page. Please don't forget that. The magnetic field here, dot dot, is out of the page. When something is crossed, if it's current, it is going into the board. If it's magnetic field, it is going into the board. I'm just trying to remind you. And when something is dot dot, it is coming out of the board. Let's go back to our solenoid. Our solenoid, or before the solenoid, let's look at this single wire carrying current. If I do this, it means on this side magnetic field is going in, and on this side it is coming out, because it is this. Look at the 3D thing, going out. Please don't forget. And this one is like this. Magnetic field is going in this way, going in this way, and it's coming out the other way, coming out this way. Please don't forget that. like this. So don't forget that. So you may see it like this in some exams instead of this. So it may be represented like that. That means it's a circular thing. It's a circular thing. It comes out here, it enters here. It's a circular thing around that wire. Let's look at that of solenoid. I still have solenoid on the board. Before I go into solenoid, please don't forget when we're talking about the length of the conductor, know that the length we are talking about is the length present in the magnetic field, not the entire length. The amount of the length inside the magnetic field is what we are talking about. So let's look at this. If I'm talking about solenoid, look at it. I'm saying, look at it. Look at it. This is different. The current is going into the board. Current, not magnetic field, going into the board. And here is coming out of the board. It's coming out of the board. When I'm talking about this magnetic field here, if I hold it like this, is going into the board here and it's coming out here like that. And this one is this way, going in here and coming out here. Please do not forget these little things. So in my next class, I'll be talking about some experiments on the Motor effect, and I'll talk about few instruments that we have using the Motor effect. So student, this is where I'm going to stop tonight. And if you have any question, do not hesitate to contact me through my email or through the admin. You will be your reply you get to you within 24 to 48 hours, depending on the nature of your reply. Your reply may be in a video form. We also send back another video to you for the reply. So students, this is where I call it a day. Good day and God bless.